Perfect. Thank
Okay,
you.
great. So our next speaker is Lisa Lehmann, who is going to be telling us how we can detect solar-like magnetic cycles with ZDI. And as before, I'll give you a 3-minute warning from the end. Please take it away.
Thank you, Victor. So hi, I'm Lisa Lehmann. I'm a postdoc at the IRAP in Toulouse, working in the group of Jean-François Donati right now, where I analyze spiro data of T-Tauri stars, meaning I determine their ZDI maps and analyze their activity using the spiro observed spectral polarimetric spectra. But today I want to show you the final results of a project I started doing my PhD at the University of St. Andrews with Gaty Hussein and my former supervisor Moira Jardin, and our collaborators Duncan McKay and Alini Vidotto. And we investigated how our own sun would look like observed as a star through a whole solar cycle, and what would be the best strategy to detect solar-like activity cycles using ZDI and a magnetic field parameter-based analysis. And on the right in the little video, you show kind of a little teaser. So on the top, you see the original input map, so the full resolved solar map, and on the bottom, the corresponding ZDI map as it evolves over time, over 15 years. So during my PhD, I worked with magnetic flux transport simulations based on the sun from Duncan McKay from the NAF Institute in St. Andrews, and his simulation connects a photospheric flux transport model with a non-potential corona evolution using the magnetofrictional technique. The results are 3D magnetic field maps reaching from the stellar surface up to the corona. And what does this exactly mean is, so on the photosphere we emerge bipolar spots, so really as a vector magnetic field having the radial, azimuthal and meridional component, and their properties were extracted from solar observations, so the range of latitudes, magnetic flux and time between two emergence were extracted from solar observations. And on the stellar surface, the magnetic field evolves then under the influence of differential rotation, meridional flow, and diffusion. The magnetofrictional technique now enables us to link the photosphere to the upper atmosphere by introducing a velocity parallel to the Lorentz force, so that the changing photospheric magnetic field is therefore vectored through the upper atmosphere up to the corona. The dataset I present today is based on the work of Yates and McKay in 2012, where they simulated a whole stellar cycle. So Anthony Yates was extracting the properties of emergent active regions out of synoptic maps observed by the National Solar Observatory Kitt Peak, covering over 15 years. And these emergence properties were used to simulate the solar vector magnetic field from the photosphere to the corona in 1996 up to 2011. And this is the big advantage, that we really have the vector magnetic field, because from the observations until then, before the new STO started, we only had the radial component and not the azimuthal and meridional ones. So the picture on the top shows the butterfly diagram of the observations and below from the simulations. And the next step, I used now the fully resolved surface magnetic field maps to model the Stokes INV profiles, assuming a rotation period of 27 days and an inclination of 60 degrees, which gives you a V-SUN-I of 1.62 kilometers per second. So our sun is really a very slow rotator. We had some Gaussian noise, which correspond to 10% of the maximum amplitude. And then I used the ZDI code provided by Gaty Hussein to determine the ZDI maps for 41 maps of all of these simulations. And I would like to show you one example map over here. So here you see the input, the full resolved input simulations, so the radial, azimuthal, and meridional field. And this is the corresponding Stokes V profile we get from this map. We expect to see something like that. So this is the large-scale field of this simulation. And on the right, you see what actually ZDI sees. So we we find that the northern hemisphere features of the magnetic field are quite well recovered by ZDI, but of course, due to the inclination, we are missing the southern hemisphere features. And we also found that ZDI is reconstructing less magnetic field than we would expect from the large-scale field of the input simulations. So let's have a look now in the whole sample. So first I will speak about the variation of the magnetic field with time, and later I will present the solar cycle 23 in context of other cool stars observation using the S-index. So let's start with answering the question, how to detect a solar-like activity cycle, or what would be the best parameters to check? And first I checked the total magnetic energy. So on the left, you see that I'm plotting the mean squared average of the corresponding to the total magnetic energy here over time for the simulations, and I decomposed them in the spherical harmonics using Alini's equation. So each L mode corresponds to a different length scale. So L equals 1 corresponds to the dipole, which is plotted in blue, L equals 2 to the quadrupole, which is plotted in orange, and L equals 3 to 27 is in this greenish color. So as you see, if I'm showing you the maps here, if we go to including higher and higher L modes, then we are getting more sensitive to smaller and smaller field structures. But as the sun is really such a slow rotator, we are restricted to L modes up to L equals 3 or 5 to the dark green points here. But the simulations do very well, so as we expect, the dipole mode is decreasing during the activity maximum, where the dipole should be weakest, while the quadrupolar mode is maximum as found by Mark de Rosa in 2012 for the Sun. And if we have the full resolved map, we see that the magnetic energy follows the trend with sunspot number I plotted here in black. So on the right, you see a snapshot for the ZDI reconstruction. So as I said, I reconstructed in total 41 maps, but you would be very lucky to get such a very dense sample. So let's say we have good luck and have now 8 successful observations with ZDI. We could see something like that. So we have something like a maximum and a minimum, so good luck. But maybe I found if you choose a different map, then you get something like this. So it looks like shifted in phase or just a flat distribution. So this really highlights that the total magnetic energy is varying a lot for the sun, especially during the maximum. So to get more meaningful result, I binned the data in 8 different bins equally spaced in time and draw 100 times 8 maps and determine the mean and standard derivation. And you see on average, it's just a very flat distribution for the ZDI reconstructions. The dipole mode shows the largest variation, but really the total magnetic energy is not a good way to track solar-like activity cycles. Far better it is if you go to the single magnetic field components, especially the axisymmetric and non-axisymmetric magnetic energy turned out to be very, very nicely recovered by ZDI. So you see for the large-scale field, the simulation shows this drop for during the activity maximum, which is well recovered by ZDI. And for the non-axisymmetric field, you see that also the large-scale field, so the dark green points, follows a trend of sunspot number, and ZDI recovers this very nicely here. Even better it is if you go to the fractions of the axisymmetric magnetic energy. So we recommend to focus more on fractions than actually energy values, as they are likely to be more robust and are less affected or not at all by the offset to lower magnetic energies we reported for ZDI detections in solar-like stars in our previous publications. So here I show the fraction of axisymmetric field for including the L mode 1, 2, 3. And you see they are covering the whole range. So we are really getting fractions from nearly 1 to 0, and ZDI is beautiful recovering this trend. So really nice. So the fraction of axisymmetric field is a very good tracer for solar-like activity cycles. What is about the toroidal field? So the fraction of toroidal field is not such a good choice to check solar-like activity cycles. Sandra Jeffers and Victor C. showed that stars with cycles show predominantly poloidal fields, and the sun also shows only very low values of toroidal energy. So we see that during the activity maximum, there is an increase in the fraction of toroidal field recovered with ZDI, but there's a large spread. And you can use the fraction of toroidal field to confirm the detection of the activity maximum, as you would expect the toroidal fraction to be maximum as well. But at all, this is not such a good choice to trace solar-like cycles. Maybe for stars that are more active where the toroidal fraction is higher. But yeah, it's worth to check. A different thing that was very surprising, or we were very lucky to find this result, is that we found that ZTI can recover important dynamo modes. So the most important mode is the radial axis symmetric dipole mode, so for L equals 1 and M equals 0, which is displayed in blue over here. So we see how the dipole really decreases as we are approaching the maximum, gets 0, and flipping its polarity and establishing again with the opposite polarity, getting its maximum during the decreasing and minimum phase, and vanishes again as towards the new solar cycle 24. The ZDI maps also show this trend very nicely. So for low active stars that are slow rotators observed with an inclination of 60 degrees, we are pretty sure that ZDI we can reconstruct this mode correctly. If we look at the orange points, which are the radial axisymmetric quadrupolar mode, which should behave in antiphase to the dipole mode, we see we have more variation. It's not as high in amplitude, and yeah, ZDI is getting the main trend, but is affected by short time variations. Another mode that's very worth looking at is the toroidal axisymmetric quadrupolar mode. We found that even if the toroidal field is pretty weak on the Sun, this mode is answering to the global properties of the small-scale flux emergence. That means to the population of the active latitudes. So the little icons you see here are showing how the dominant poloidal mode, so the dipole in blue, and the dominant toroidal mode, the red arrows here, are behaving during a solar cycle. And the gamma coefficient of the equation for L equals 2, M equals 0 is really capturing this. So during the increasing phase, we see the maximum values as the active regions appear at mid-latitude range of opposite polarity of the two hemispheres. As the cycle progresses, the latitude of emergence of the active region decreases and it gets fainter and fainter until there are no signals at all in this mode any longer, as we have no active regions. When the new cycle starts with opposite polarity, we see that this number is increasing again. You may notice that the transition between solar cycle 22 and 23 is quite differently from the transition between 23 and 24. And we think this is due to the unusual long minimum that occurs in 2008, 9, and 10. So between 1996 and 2000, we noticed that we have the situation that on the near the equator at low latitude range, we still have active region showing the polarity of solar cycle 22, while on the mid-latitude range, already the star spots of solar cycle 23 appear, and at some point they just take over and dominate the polarity. While here between solar cycle 23 and 24, we have the situation that we're approaching this very long minimum. We have nearly no or no sunspot for a year or longer, so that we are really getting to 0 in this mode before the new cycle starts again. The very promising thing is that ZDI gets this trend more or less. You would need a very good sample in time to really be sure to see this trend. but it looks so promising that it would be very, very interesting to check other stars if this mode is also giving you some hints about the population of active latitudes, or if other stars don't have active latitudes or behave differently in or the star spot population behave differently here. So speaking about other stars, let's have a look how solar cycle 23 behaves in relation to them. So I'm showing here in gray the observations as collected by Victor C. in 2015, plotting the toroidal energy over the poloidal energy. And our simulations are the circle dots here, which lie in the same region as other solar-like stars, and the triangles are their SETI reconstructions. You see they are about 1 magnitude lower, as we already found in my previous publications, but they recover the trend with sunspot number very nicely. So you see during the minimum where the sunspot number, which is the color code here, there's a drastic drop in the toroidal energy here. If we look at the maps individually, I also use the confusogram as introduced by Emma. So the symbol size is related to the fields, to the magnetic energy. So big symbols show strong fields and smaller ones weaker fields. The color, how poloidal or toroidal the field is, and the shape, how axis or non-axis symmetric it is. So in our sample, SETI is doing a good job. Of course, the symbols are a bit smaller. That means we are recovering less magnetic energy, as I mentioned before. And during the activity maximum, we also see that they tend to be less axis symmetric and less poloidal, as the input maps suggest. But a bit below a sunspot number of 100, SETI is really doing a great job in recovering the large-scale field topology. Until now, I was only speaking about about the magnetic energy, but what is about the surface average large-scale field?
3 minutes, Lisa.
Thank you. As we can't measure sunspot number for other stars, I'm swapping here to S-index on the x-axis, which we found correlates linear to sunspot number. Is still in color coding in sunspot number. Of course, there's some spread, but it's a good choice to go here for S-index. So we see that for ZTI, this is only a flat distribution, so ranging from 0.8 to 2.4 Gauss here. Also, the input maps show quite a flat one, but with an upper envelope. But really here we see that the sun is such a slow rotator that even if we have high number of sunspots, or especially if we have high number of sunspots, the magnetic polarities are just canceling within the resolution elements. For the poloidal energy, it's kind of the similar picture, but for the toroidal energy, we see more interesting features popping up. So here we see that for higher S-index, there's a an increasing trend with S-index, which is recovered by ZTI within the arrows, which is very cool. So it would be nice to see if other stars also show a trend, an increasing trend with sunspot number of the toroidal energy or not. And we see something, a region of for low S-index where it just sharply drops. This is even more clear if we go to the non-axis symmetric energy, and this S-index corresponds to sunspot number of 50, and it shows like below this sunspot number, the active region are not longer able to affect the large-scale field, so that we just see the drop here. Last but not least, I would like to show you this nice linear correlation between the axis energy fraction and the S-index, which is very beautifully recovered by ZTI. And I think we can use this slope as an indicator for cycle strength, because as I was overplotting solar cycle 24, where I have observation thanks to Alini, which are just lying on my desk, I noticed that if you would plot now also a trend line here, that this line would be steeper. And I checked with the data from 61SIG-A using a suggestion of publication from 2016 and 18, where she was able to observe 61SIG-A over one magnetic cycle. That means two activity cycles where the first one was stronger in S-index and the second one was weaker. And we see the same pattern if we plot the fraction of axisymmetric field over S-index. So this is also a really, really encouraging result we see here. So to summarize, we recommend if you want to observe solar-like cycles, don't check or don't use the total magnetic energy or the average field, really check the axisymmetric fraction and axis and non-axisymmetric energy. And also it would be worth looking at the toroidal fraction if you see the maximum occurring at the maximum of the cycle. We also found that ZDI can recover important dynamo modes and that plotting the fraction of axisymmetric energy over S-index could be used as an indicator for cycle strength. The results are published in this paper here. You can find it on ADS or under this archive link, and I thank you very much.
Thank you, Lisa. So if anyone has any questions, again, please raise your hand or say so in the chat. Got a question from Julian.
Yeah, can you hear me?
Yes.
Yes.
Yeah, great. Well, it's more a comment than a question, but yeah, thank you, Lisa. It was a very nice talk, and I won't say it's really great work, because it's true that we know for some time that obviously ZDI works well for active very active stars with a high V sin I when you have good sampling. We know also that there are some limitations, but it's really good to arrive to this stage where really we have a more quantitative understanding of really what we can recover for slowly rotating stars like the sun. And yeah, this is very, very useful, and I'm really confident that we can make good use of this information in the coming years for the coming studies to really get a deeper understanding on the cycles and what we can really extract from the ZDI studies. So that's really great to see that.
Yeah, it's really nice to really check for these very slow rotators where we are so limited in resolution what you can get out of the different magnetic properties we get from the ZDI maps.
Mm-hmm. And it's even I mean, more interesting in the sense that it's true that now we are going to well, we have been already on these moderately active solar type stars, but also now we are addressing a lot of M dwarfs also, and for these stars, even when they are very active, the V sin I's are low. So it's really good to have this more, yeah, as I was saying, quantitative, accurate idea of what we can really recover. So very nice.
And we have a question from Mayuk. Sorry if I pronounced your name wrong.
Yeah, it was correct. Hi, very nice talk. I just have a small question about. So you showed your radial azimuthal maps on slide 5. Can you please show that slide?
Sorry.
Can you please show your slide number 5 where you had the maps of your radial azimuthal and fields?
Yes, of course. Yes, here.
Yeah, so I'm wondering, so using your, was this using your surface flux transport code? Because I'm wondering whether, so how you obtain the B meridional and B azimuthal? Aren't most SFTs just solved for BR?
Yes, most of them are, but this is really the strength of the work from Duncan McKay and his collaborators, that they really were able to get the azimuth and meridional field. So I really would recommend you to look at his work so that you can see how they do this.
Okay, thank you.
Any other questions? Quick questions? If not, let's thank. Oh, very quick question from Timu.
Okay, thanks. So would you say that these results also apply to some solar type stars which are much more rapid rotators and had much stronger magnetic fields than the Sun?
Yes, it would be very worth checking this, how they differ, especially how the toroidal field is doing for them. And it is kind of a different framework that we are looking then, because we really need to keep in mind at which resolution are we looking at. So as for this faster rotator, of course, we are then, for example, getting here in the higher almost. So it would be worth, even if we have the faster rotator, to really decompose then in the different almodes to check if they are behaving in the same manner like the Sun, or if they don't do that. So, yeah, but we have to keep in mind at which resolution are we looking with the ZDI maps.
Okay, well, let's thank Lisa again. And let me